Hey, it's my turn, and this time I'm gonna tell you like another project I brought from my postdoc training to Iowa and finished here. So also in this, I think the common theme of this study and the study I present this morning is we wanted to study the interaction between long-term memory learning and cognitive control. So this time we are still looking at associative memories, but instead of looking at spatial context and task demands, we are looking at associations between items and cognitive control demand. So here is a idea. So that say in real life, say if I drove on this really busy overpass one time and I could make an association that this overpass is associated with a high cognitive control demand. So next time when I see this overpass far away, and then I can use that as a visual cue to retrieve its associated high cognitive control demand, so that I can proactively increase my control level in anticipation of this busy overpass. So some of our previous work and as well as others, including Julie's work, have shown that in laboratory, this kind of item-specific proportion congruency effect. And yeah, so here, in order to study this kind of a question, to using neuroimaging, so we again paired the similar behavioral paradigm with high density EEG. So this is the behavioral design we have. So this is a typical item-specific proportion congruency effect or ISPC design. And the task is that on each trial, the participants will see a tool image and a name of a tool. They don't necessarily agree. When they do agree, and this is a congruent trial. And also during the task, the participants were asked to respond to the tool image by using a button press. So we before the task, we have them trained on the mapping between the images and the responses. So yeah, if the word and the image lead to a same response, it's a congruent trial. And if they lead to different responses, this is an incongruent trial. And then in incongruent trial, higher cognitive control is needed in order to suppress the processing of the word and to enhance the processing of the tool image in order to produce the correct response. So to manipulate the associations between individual tool images, which are our items, and the cognitive control demand. So out of the 4 tool images we have, we presented 2 of them in mostly congruent trials. So in other words, for those two tools, if the participants see them, they were more likely to perform a congruent trial, which requires lower cognitive control demand. And for the other 2, we presented those 2 tools in mostly incongruent trials. And then in this case, when participants see those 2 tools, and then they were most likely to be dealing with an incongruent trial, which requires higher control demand. So therefore, those 2 tools are associated with low control demand, and those 2 tools are associated with high control demand. So that's the behavioral manipulation, and indeed in behavioral data, we find that this manipulation indeed modulates subject's response time, as already been demonstrated in previous studies. So we are interested in what's happening in the brain. So basically, we take an idea from the dual mechanisms of control theory, such that say this is a time course within a trial, and then this is a time point in which the actual control demand, in other words, whether this trial is congruent or incongruent, that is detected in from the stimulus. So from this point on, the brain is going to use the actual control demand to guide our cognitive control to generate a response. But before that, because we have this association, so this the tool image can be used as a cue to retrieve its associated associated cognitive control demand. In other words, prior to the detection of the actual control demand, the associated control demand will be, like this interim guide of cognitive control. And mapping onto this design, so we would expect that before the actual control uh, demand is detected, we would see a pure main effect of the associated cognitive control demand. So that's the difference between the 25% and the 75%. And after the actual control demand is detected, so there is this process of taking over. So new control demand takes over the old ones. Therefore, we would expect an interaction effect reflecting this taking over. So this is our hypothesis, and then we look into the brain. And first of all, for the main effect of the associated control demand, we found that in those left parietal frontal channels, and this is the time frequency analysis. So especially in this alpha band, so there is this main effect of the main effect of associated cognitive control demand, such that alpha power is lower when the associated control demand is higher. And this is peaked around 200 milliseconds following the onset of the stimulus. Then for this interaction effect, we did basically all analysis are like a whole brain search clusters ratio analysis. So yeah. So for this interaction effect, we found that the most prominent component is the one in theta band and in posterior channels. So this effect is peaked around 350 milliseconds following the onset of the stimulus. You might see that maybe there are those other components that might also be statistically significant. So we tested all of those, and this one is the best because this one does not only show this interaction effect and the size of this interaction effect on each trial, it can predict the response time in that trial. So it also has this component of brain behavioral correlation. So we think that might be our best candidate reflecting this interaction. So yeah, just by saying that this peaks at 200 milliseconds, this peaks at 350 milliseconds, maybe not enough to establish the temporal order. So we actually extracted each of those two components and get their temporal distribution. So that's a proportion of channel frequency combinations at each time point. And then we did a bootstrapping non-parametric statistical analysis on those two distributions over the participants, and indeed show that this distribution, which represents the component of the main effect of the associated control demand, that one indeed precedes the interaction effect. So kind of support our hypothesis that cognitive control is first driven by the retrieved associated control demand, and after the actual control demand is detected, then the actual control demand takes over. Okay. So that's our first part of the study, just to look into the within trial temporal dynamics of the memory guided cognitive control. Then we also want to look further, because one cool thing about associative memory is that we can learn without any direct experience through our associations. What do I mean by that? What that means this generalization that David talked in his talk. So say like in our case, if we have three items, A, B, and C, and first imagine you learn A and B are associated, and then you learn that A and C are also associated. Then I ask you if are B and C associated, even though you don't have any direct experience of B and C being associated, but through their common associate A, you might have this indirect link that B can go to C through A, so that B and C might be associated. So that's kind of generalization, or a type of learning without direct experience. So yeah, in other types of tasks, say in memory tasks, and in decision-making tasks has been shown that this generalization effect exists. And then also in the field of cognitive control, yeah, there are some other works and also showing this effect. So one thing we are particularly interested in is when does this generalization occur? So it could be occur during encoding or during retrieval, and both have some empirical support. And what do I mean by generalization during encoding and retrieval? So the idea is that if the generalization occurs during encoding, say, then that's going to be when we are learning the ABs and ACs. So in other words, while we are learning the AB and AC associations, A, B, and C will be integrated into a bigger integrated memory trace. And in that case, because B and C have been integrated, so B and C are associated automatically. So that's during encoding. And this is before we probe the participants whether B and C are associated. So that's a different, that's an important point. And if a generalization occurs during retrieval, that means during the learning of the ABs and AC, then there won't be any integration. So the generalization occurs when we ask the participants if B and C are associated. So in this case, B as an input will retrieve its associated A, and C as another input will also retrieve its associated A. So this A being commonly retrieved, so that's gonna establish a path for B and C to be linked together. And importantly, again, this occurs after or during the probe of the BC association. And we want to kind of test whether this generalization occurs during encoding or during retrieval. And in order to do that, we need a learning of both ABs and ACs. So what I just showed you is actually just 1/3 of the experimental design. So the full design looks like this. So it has 3 phases. And in the first phase, we associated each individual tool images to a unique landmark image. So you can think those tool images as 8 items and the landmark images as B items. So in the first phase, we established the AB association. And then in the second phase, the tools are associated with different cognitive control demand. So the cognitive control demand can be thought as C items. So in this phase, it is AC association. And finally, in the last test phase, we want to look at if we can establish or having the generalization of the BC, which is the association between the landmark and the cognitive control demand, that is obtained through this transfer. So control demand linked to tool and then transferred to the tool's associated landmark image. So that's going to be what we will be testing. And then in this test, so we used a similar kind of a Stroop task, but this time we used landmarks, names, and images as a stimuli. And importantly, we are focusing on this diagnosis stimuli, like Julie mentioned. So those for those 2 stimuli, they are neutral, so there's no difference in terms of their presented context or the proportion of congruency those 2 stimuli are presented in. So if there is any difference, it has to be come from the it has to come from the associations with the tools or the generalization effect. So indeed, behaviorally, we show that there is such a generalization effect. This replicates those previous studies showing the transfer or generalization in cognitive control. And then we further wanted to to look into the brain and see if there's any neural evidence suggesting this generalization. So the first thing we test is to take out this main effect of associated control demand. So that is from our training phase. So the phase participants learned the tool and its associated control demand. So we have this component showing the this associate or kind of reflecting this association So we use this to the as a ROI and apply this to the test phase data. So the idea is that if the association indeed is generalized to the test phase, and then the same generalized association effect should be observed as well in the same component. And indeed, we observed this effect. So that's the first part to show that generalization indeed happens in the brain. And then going back to my question of when did it happen? So we start with the theory of integrative encoding, or in other words, generalization occurred during the encoding or during learning. And this is our sequences of rounds. So the associations are those two landmark association learning rounds. So as you can see, we interleaved the association of the ABs and ACs rounds. So that gives us the chance to see, to use the first two rounds as baseline, because in the first two rounds, the participants hadn't had experience for the cognitive control demand. So they only have the ABs. So for those two rounds, we know for sure that no generalization could happen. And then for the later association rounds, because they occurred following the first two training rounds, so they have both ACs and ABs. So generalization could happen in those four rounds. Therefore, we can compare neural activity in those four rounds to the first two rounds. So that's going to be one contrast we will use. And then within the association trial, so participants will first see a tool image, and the tool image will be followed by its paired landmark image. And in this case, our hypothesis is that when the participants see this tool image, it's going to retrieve its associated control demand. And both the tool image and the associated control demand, their neural representations will linger for a while until the landmark image is presented. So by the time the landmark image is presented, the brain has simultaneous representation for all the three pieces: the control demand, the tool image, and the landmark image. So this allows the brain to integrate those three pieces of information and to generalize. So this is the second part of our contrast. And by taking those two contrasts together, and then we have this interaction effect where we look for. Then we'll get into the EEG data. Again, it's a time frequency analysis. And what we found is that this interaction effect is shown in medial frontal channels peaked around maybe 350 milliseconds post the presentation of the landmark. Excuse me. So yeah, and also the direction of the interaction is also what we expected, such that the decrease of alpha power has most decrease in the later association trials and after the presentation of the landmark image, or in other words, that is where we hypothesize that generalization will occur. So that has a higher drop in alpha power. Of course, this if we think this is a generalization effect, it may not be enough. Right? If this is indeed when generalization occurred, then you should affect the generalization effect during test. Right? So basically, you can think of this as the retrieved generalization effect, and this can be the generalization occurred, so the time generalization occurred. Then this two should be positively correlated, such that if you have a stronger generalization during learning, then you should have a stronger retrieval of generalization. So in order to test this, we did a cross-participant correlation of the strengths of those two components. So we had 43 participants, so we have some power to do this analysis, and indeed we find this positive correlation between the two components. Now, one thing is kind of interesting is that if we switch this component from the same pairs to another pair, say if on the x-axis it is encoding the generalization strings. Let's just say this is generalization strings for the pair of can opener and the White House. And then on the y-axis, it's a retrieval generalization effect for, say, Jefferson Memorial and the hammer. And then they actually will show a negative correlation, which kind of hints that maybe there is some competition going on if we concurrently generalize multiple pairs or trials. So yeah, just to summarize, in this study, we first look into within trial temporal dynamics of memory guided proactive control. So basically, the retrieval of the associated control demand precedes the actual control demand in guiding our cognitive control. And then we look into the generalization using this ABAC kind of design, and then we find that the generalization occurs during encoding. It's automatically, I say it's automatic because it occurs before we probe the association in the test phase. Therefore, this is kind of a free knowledge we get while we are learning the AB and AC association. So we learn the BC for free during this process, and this generalization seems to be involving this alpha decrease in the medial frontal channels. So that's all I have for this study. And finally, I'd like to again thank my advisor Anthony Wagner and my colleagues Anna and Pam, and also my collaborators from Lund University in Sweden, Mikael and Inish. And, again,